Alright, crazy kids, here's your second part of your electron configuration lecture. In this lecture, we're going to be going through the three different types of electron configuration. Remember, electron configuration is just talking about the probable locations of electrons, nothing crazy. Before we get into those three different types, which are called orbital notation, exponential notation, and noble gas configuration, I need you to show you how the Aufbau principle actually matches the periodic table. Now, we kind of get that electrons occupy the lowest energy level that can accept them and then work their way up to higher energy levels. And that's the Aufbau principle. We have this electron energy ladder type thing, which shows us the lowest possible location is 1s, and according to this one, the highest location is 7p. Realize there's locations above that, but we don't really need to worry about those excited states for now. What we do need to worry about is how these two things match. If we look at the Aufbau principle, you can see it right underneath it. I've written 2 electrons per space orbital. That's something important to remember. So what I mean by that is every orbital can occupy 2 electrons, one spinning one direction and one spinning the other direction. In our first possible location, 1s, or energy level 1 in the s orientation, well, s shape and there's only one possible orientation, I can fit 2 electrons. After those 2 electrons fill up 1s, we should see that they fill up 2s. And then they go to 2p and then 3s. Okay, this is the electron energy ladder. That's the Aufbau principle. We get that. What we probably don't get is that 1s is actually located here. 1s. This helium atom should actually be over here in terms of its electron configuration. It's located in group 18 because it's very similar to all the other elements in 18, but in reality, in terms of electron configuration, it should be over there. So all of these elements, their last electron is located in the s orbital. All of these 2p, this would be 2p right here. See this 2 and then p. So all of these elements, their last electron is located in the 2p orbital. For d, here's 3d. This right here is 3d. Now you're going to say, but it's in period 4, Mr. Estes. But d is n-1, so period minus n1. So all of these elements, their last electron is located in the 3d orbital. And then finally, 4f, right here is 4f. Well, not lanthanum. Lanthanum is actually in 5d. But these elements are located in the 4f orbital. Their electrons, the very last electron, the highest energy electron, is located in the 4f. Now, d is n-1, so 6 minus 2 is 4, and all of these elements right here are smashed in this little location right here, which will be 4f. At the very top of my Aufbau principle, you can see that I put 7p. At the very last element, 1 to 18, is in 7p. Here's 7, here's p. So that's really the highest energy that you're going to see in terms of a ground state of electron. There are locations that are above that, but we don't really have to worry about those right now. Hopefully you can kind of see how the periodic table matches your Aufbau principle. And as you're filling them up, you get more and more electrons. If you've noticed, I also wrote underneath here the number of electrons in each one of those possible locations. That matches the periodic table as well. If we look here, 2 electrons in S, notice how the S block is only 2 elements wide. So this would be S1 and S2 the whole way up. Here, 6 electrons in P. P has 3 different orientations, 2 electrons per orientation or per space orbital, totaling 6 electrons. P block, we can see, is 6 elements wide, matching the 6 electrons that are going to fit in that location. For D, D has 5 different orientations, a total of 10 electrons, 2 electrons per orientation. Look at D block, it's 10 elements wide. All this information should be matching. And finally, F, 7 different orientations, 2 electrons per orientation, total of 14 electrons. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Lithium and actinium actually belong in D block. But those are the 7 different orientations filling up 14 electrons for F block. That's a lot of information. I'm happy to explain that more. But for right now, let's jump into how do we actually show orbital notation or electron configuration. For orbital notation, what we're going to be doing is drawing a space for each different orbital present. You're going to use arrows to represent electrons. So if I want to show all the probable locations for, let's say, aluminum, for those 13 electrons, atomic number 13, if it's neutral, I would have 13 electrons to deal with. I'm going to start at the very bottom, 1s, and work my way up until I hit my magical number of 13 electrons. So here I'm going to draw a line indicating an orbital. Underneath it, I'm going to draw 1s, energy level 1, and then s for the shape of the orbital, and then I'm going to put an electron in it. So here's my first electron. That shows that the very first electron is going to be in 1s. The next electron, because s can hold 2 electrons, is going to go the other direction, spinning down. Those are your first 2 electrons. Have I shown all 13 electrons? No, I have not. I still have 11 more to go. So after 1s comes 2s. I'm going to draw a line for the orbital. I'm going to write 2s underneath it, and then I'm going to fill them in one at a time. Now I've shown 4 electrons for the orbital notation of aluminum. This is aluminum. I should probably write that down. 13 electrons. I've shown 4 electrons. We got 9 more to go. Where do we go after 2s? Oh, 2p. Remember, 2p actually has 3 different orientations. 2px, 2py, and 2pz. One orbital for each orientation. I'm going to fill these in one at a time. Remember, 1 electron per space orbital before doubling. So I'm going to show that as electron number 5, 6, 7, 8, 9, 10. I fill them in one at a time before I double. Now I've shown 10 electrons for aluminum. Am I done? No, I am not. I still have to show 3 more locations. So after 2p, if I continue on up here, I get to 3s. So 3s only has 1 orientation, 1 orbital. I've drawn 1 line, shown that location. I'm going to put 2 electrons in 3s. Am I done? I've got 1 left. That last one after 3s here is going to hit 3p. There it is. So I'm drawing 3px, 3py, and 3pz. You might say, well, is it required? Because I only have 1 left. I know it's going to go right here. Do I have to show these other locations? And the answer is yes, you do. These are like seats in a car. You have to show them even though they're unoccupied. This would be the whole car. Shown here, I have to do it. Fun thing about D, if you recall, there's 5 different orientations for D. You don't have to show orbital notation for D. I would never give you an element that big for orbital notation. It would just be silly. So don't worry about D. But for P, you have to show Px, Py, and Pz. Okay. Now, am I done? Yes, I'm done. I've shown the 13 probable locations for electrons for aluminum. Do I know I have the right answer? Yes, I do. And I can double check my work because I can see that this is 3p and that there's 1 electron in it. Let's take a look. Here's 3p1. 3p1. Same information. Okay? So I've shown the 13 probable locations for electrons. The last location is in 3p1, the same location aluminum is on the periodic table. It's got pretty messy. Let's see if we can clean it up a little bit before we go on our next one. It's got very messy. All right, this is looking a lot better. Wow, that got very, very messy. All right, ooh, this one's kind of a mess. Let's see if I can salvage this a little bit. Oh yeah, here we go. Oops. Be a lot easier just on a whiteboard. I could just erase this, but here we go. So that's aluminum orbital notation. Before we jump into exponential notation, let's do another orbital notation just to make sure you guys get the concept of it. How about we do, oh, I don't know. How about lithium? Something nice and easy. Now, lithium, I know it's going to end in 2s1. How do I know that right away? Well, look at its location. Here's the 2. This is S block, and it's the first element in S block. So I know the very final thing is going to be 2s1. All right, it's going to look like that because that's the last location. Let's see if that information matches up. I got 3 electrons to work with. So lithium, 3 electrons. I'm going to start with 1s. I'm going to show the 2 electrons in 1s. I'm going to do my arrows very quick hand like that. If you want to, you can make them like this over and over and over, but this is perfectly fine arrow in my book. And then after 1s, according to our off-brow principle, because we're going up, I hit 2s, there it is. Here's my 2s, and I'm going to put 1 electron in there. So those are the 3 electrons for the orbital notation of lithium. Okay, let's get rid of this stuff, clean this up, and we will show you now how to transform orbital notation into a shorthand version called exponential notation. For exponential notation, I will do aluminum with 13 electrons. You might have guessed it, electrons are now exponents, not arrows. So I'm going to show the same information. However, I don't need to show the orientations. I just need to show the actual orbitals. Meaning, with aluminum, I'm going to start with my 1s, and I'm going to put an exponent of 2. That is the same information shown here. Just a shorthand version of it. You might say, well, why is orbital notation important? Trust me, it's important. When we talk about bonding, it's going to kind of show you how bonds actually occur. But for now, you'll think it's a waste of your time. I assure you it's not. All right, so those 2 pieces of information were the same. Actually, I'll leave that like that. Our next one, according to our electron energy, 1s to 2s, 2p to 3s. Okay, we're following that energy up. So the next one's 2s. I'm going to put my 2 electrons in there. Now I'm going to put my 2p6. Like I said, you don't have to show the orientations for exponential notation. You just need to show the actual orbital, the shape of the orbital. So here we have the same information. Let's do 2s. There's 2s. And now we have 2p6. All of this information is the same, but now I'm just using an exponent for those electrons. After that is going to become 3s2. Here's the same information for 3s2 right there. And finally, I need to put 3p1 down. I don't need to put all 3 of the houses because all that information is stored in that actual just 3p1. And that will be your correct answer for your exponential notation for aluminum. Now, let's make sure this makes sense. 3p1, that's our final location. Once again, here's p block over here. Here's 3, and aluminum's right there. So 3p in the first element in the p block. That relates to 3p1. The 3, this is one of your quantum numbers. That's the shell. That's your energy level, third energy level. The p is the orientation and, in this case, the shape of the orbital. And then finally, your exponent is how many electrons are actually located there. This is the triad of information we're trying to convey. All right. Let's do lithium just to make sure we have the same piece of information. Lithium with our 3 electrons would be 1s2, 2s1. Oh, why did I write 2p? Oh, S is terrible. 2s1. There we go. Same thing. Noble gas configuration is a little bit trickier. All right. For noble gas configuration, it's an even more shorthand version of exponential notation in that we only list the electrons in the very outermost shell, which are called your valence electrons, or the outer shell electrons. So those are the electrons that can be lost, shared, or gained when chemical bonding actually occurs. We'll do aluminum, and I'll show you how to actually show those 13 electrons now. So for noble gas configuration, the first thing we need to do is locate the noble gas that precedes aluminum, comes before it. Over here, you have all your noble gases, group 18. If you didn't know that, now you know. And we're looking for the noble gas that comes before aluminum. Here it is, neon. Notice how neon has 10 electrons. For noble gas configuration, I need to show my 13 electrons. I'm going to put neon in brackets. By putting neon in brackets, I'm showing those 10 locations for the electrons. Now all I have to worry about is the electrons that come after neon. Let's see here. So after neon, oh, here's 3s. And then I have 2 electrons in 3s. So basically what you've done with noble gas configuration is you've shown all these electrons that lead up to 3s. All these ones right here. That would be equal to Ne in brackets. Those are those 10 electrons. Now I'm going to start with 3s, continue until I hit my element that I need. So there's my 10 electrons. I'm going to do 3s, 2. S can hold 2 electrons. And then after 3s, well, let's see up here, after 3s comes 3p. There it is. And I will do 3p1. Notice how that's the same information right here. So all of this information, that is occupying the neon in brackets, a total of 10 electrons. Let's count them up. 2, 4, 10. So there's your 10 electrons. And then I have 3 electrons after that, 3 electrons after that, total of 13 electrons. There's your answer. Let's go ahead and do lithium as well for noble gas configuration. We need to locate the noble gas that precedes lithium. So here's lithium. The noble gas that precedes it would be helium. So I'm going to put helium in brackets. So once again, this is for lithium. I put helium in brackets. That took care of 2 electrons. And what comes after helium? So after helium, from number 2 to number 3, oh, that's lithium. Oh, great. Okay, well, what's the location of a lithium? 2s1. 2s1. And that information is the same information there. This is the configuration for helium. I've used brackets to show that. And I have 2s1. All right, let's just do a fun one to make sure if you guys kind of get this concept. So I'm going to do exponential notation for, I don't know, maybe lead. Pb, 82 electrons. Let's go ahead and find the last location. Let's see if this makes sense. I'm going to clean this up before we get started. Oops. Oh no. Hey, go back in time. There, here we go. Good, good, good. Gotta go a little bit smaller. Nice. All right. So lead is located right here. Let's find its last location. That's going to be 6. This is P12. So I know the very last location that I'm going to occupy is 6P2. Let's take a look at our electron energy ladder. That's way up here, 6P. I know everything before that, everything I'm drawing arrows through right now, is going to be occupied full. And then the 6P one is only going to have 2 electrons in it, or 6P2. Let's see how I do. We're going to start with 1s2, 2s2, 2P6, 3s2, 3p6, 4s2, 3d10. Oh, why did I go 3d10 there? Well, recall that after 4s, we have d, and d is n minus 1. So this location right here that I'm scribbling through is actually 3d. Just remember. And what comes after 3d? Well, I believe it's 4p. Let's check a look. Oh man, I erased it. Let's not erase it. So 3d, 4p. Okay, let's go back. We have 4p6, 5s2. Ooh, after 5s2, what are we going to have? I think it's going to be 4d10. Whoa. How do I know? Let's take a look. 5s2. Oh, yeah. Then 4d10. Perfect. That's really messy, but I think you guys could see it there. So 4d10. I've run out of space. I'm going to have to go to 4d10. And then 5p6, 6s2, 4f14. Oh boy, 5d10, 6p2. Why did I go 4d14, then 5d10, and then 6p2? So this last 4 combo here, let's take a look. I did 6s2, 4f14, 5d10, 6p2. All right, so 6s2, 4f14 is located here. That will come next. And then 5d10 will be all of those elements. And then 6s1, 6s2. And that should be a total of 82 electrons. Cool. Let's count them up. Make sure we got it right. So 2, 4, 10, 12, 18, 20, 30, 40, 50, 60, 70, 82. That's how I count. Makes sense to me. Makes sense to you? See ya.